So I need to find out where the electric field is going to be 0. And I need to ask myself where there might be solutions. Can there be a solution on the left of both charges? Is there anywhere on the left-hand side where the electric field will be 0? And the answer is no, because any positive test charge I put there is going to definitely go to the right. It's going to be attracted to both of those charges. So there can't be any solution there. What about, well, similarly, if I try to see if there's any solution over here, if I put a positive test charge anywhere there, that test charge is going to move to the left for sure, because it's attracted to both of those point charges, so there's not going to be a solution there either. So if there is a solution, it's going to be somewhere right in the middle, or like not right in the middle, but somewhere in the middle. It's actually not going to be right in the middle. It will not be right in the middle because it's going to go more towards the stronger charge. So my answer is actually going to be somewhere on the left half of the in-between section between the charges. It's not right in the middle, but it's going to be shading towards the weaker charge. And it needs to shade towards the weaker charge so that hopefully the closer distance will help make the electric field stronger to balance it all out. I'll call that point P. I'll call the Q charge or negative Q charge 1. I'll call the other one charge 2. So there's two ways I may approach this. There's the brute force way, which takes a bit longer in terms of steps. And then there's the other method involves perhaps less calculation, but more explanation. So, well, I'll show the brute force way first. The distance between charges 1 and 2 is given as 1 unit. So what I'll do is I'll label the distance from charge 1 to P as x, and then from P to charge 2, I'll label that as 1 minus x. So together they span 1 unit. And in order to have the electric field equal to 0, right at point P, I need the electric fields to balance out from the two charges. So the magnitudes of the electric fields will equal. So then I can say that KQ over x squared equals K4Q over 1 minus x squared. So that's applying the formula for electric field using x and 1 minus x for the distances, and then using q and 4q for the charges of those 2 points. And then things would cancel out. K's would cancel out, q's would cancel out, and then you're left with 1 over x squared equals 4 over 1 minus x squared. You can do some cross multiplying. And expanding. Bring everything to one. This is a quadratic equation now. And perhaps factorable. Yep, factorable. So that gives x equals a third, or x equals -1, which is inadmissible. So x is a third. So our point has to be exactly 1/3 of the way in between. So I call this brute force. it'll work. You just have to work through the algebra. In this case, it's not so bad. It's just a quadratic equation. A bit more of a conceptual approach. Here, I won't explain the full thing. I'm just going to say that because 4q is 4 times stronger than q, then the distance, the ratio in the distances has to make up for that. Okay, maybe I will write it out. I'll say balance this. So that means that x over 1 minus x, the ratio between those two distances, needs to be a half. Needs to be a half. I need charge 1 to be half the distance away from P as charge 2 is. This has got to be it's got to be a 1 to 2 ratio in terms of distance, because the distance variable is squared in the term in the equation for electric field. So 1/2 squared is 1/4, and that factor will balance out that 4 times stronger that one charge is. So that would be a much shorter way to do it mathematically. It does require some deeper explanations though. So cross multiplying this gives that linear equation, not a quadratic, just a linear equation. Bring the x's to one side, x equals 1/3. Same result.